Yep, there we go. All right. So yesterday we had all of the videos and everything was supposed to be working. It was working before I got off the correspondence with Canvas, but for some reason it still isn't working. So I'm gonna try something else to get the videos to you. I'm gonna contact them. So after class, if you walk by and see the door closed, I'm still in here. So I'll contact them and see if we can get this fixed. So every once in a while, the first week you'll just have problems like this. So unfortunately, you won't find out about it until it goes wrong for someone. So I do apologize for that, but hopefully I'll get them to get it straightened, taken care of. All right, so we're gonna go ahead and start on section 7.1. Now, 7.1, at least to me, is not as crazy as chapter 6. Well, chapter 7 is not as crazy as chapter 6, so hopefully it'll be a little bit easier to absorb because you're not dealing with any shapes or anything. So you're looking at integration by parts. Okay, it can still be tricky, but just I don't think it's as bad as chapter 6. Okay, so what if we let u of x and v of x represent two functions? Okay, so if we take the derivative with respect to x of u of x and v of x, using the product rule, we have the first times derivative of the second plus the second times the derivative of the first. And you could say u or u of x and v of x, but I'm just leaving out the x independent variable just to make it easier to follow. Okay. So we have our derivative of v with respect to x. That's just v prime of x, or we can just say v prime. So if we take the differential of that and have dx on both sides, we know that the derivative of v is equal to v prime dx. Same thing with the derivative of u with respect to x is equal to u prime of x, or just u prime. Put it in differential form, derivative of u is equal to u prime of x, or u prime dx. So we can rewrite this as the derivative with respect to x of u of x times v of x is equal to u times v prime of x. We could say dv dx plus v times u prime of x, which is du dx. Okay. So if we take the integral of each term, oh, actually, you can put it in front. Since we're going to include the v and the u. Okay. Well, we know the integral and derivative, they cancel each other out. So this is just u times v is equal to the integral of u, and the integral of v with respect to x, they cancel each other out. So you just have u dv plus the integral of v, and the integral with respect to x cancel each other out. So it's just du. So if we subtract the integral of v du from both sides, we end up with the integral of u dv is equal to uv minus the integral of v du. And that's actually your integration by parts formula. Now, with integration by parts, you don't want to just go in there and just blindly start plugging in values for your u and your v. Okay. Anyone still writing? Okay. Okay. Now you have a choice of what you're going to use for your u and your v. And they have a little bit of an acronym to help you with that. So the choice of what function you're going to make your u and which one you're going to make your v can be made using the acronym LIAT. Just think of late, but with an I thrown in there. Okay, so the L stands for logarithmic functions. The I stands for inverse trig functions. The A stands for algebraic functions. So it'd be like x squared or x to the fifth or something like that, just a regular algebraic functions. So you can think of it as kind of like powers of x. Uh-oh. For example, the T stands for trigonometric functions. And the E stands for exponential functions. Now, the higher on this list, the more likely you are to use it as your u of x. So the higher on the list, likely you're going to use it as your u or u of x. All right. Anyone still writing? Okay. So let's say, for example, if we wanted to evaluate the integral below. Let's say you want the integral of the natural log of 4x to the 5th power divided by the square root of x with respect to x. So if we rewrote this, you have the integral of the natural log of 4x to the 5th power times 1 over square root of x with respect to x. So you have a product of two functions you're trying to integrate. Okay. Now u substitution won't work because you have a u to the negative 1/2 and trying to turn that somehow into x to the, not u, x to the square root of x, or x to the negative 1/2, and you have x to the 5th. So u substitution won't really work on this one. Okay. So if we look at our list, we can see logarithmic functions. And using the LIATE, we can see the logarithmic functions comes before the algebraic function. So we're going to make our logarithmic function our u. And integration by parts, you see that u is equal to the natural log of 4x to the 5th power. And your dv is going to equal 1 over square root of x with respect to x. Okay, so you're always going to start off with finding your u and your dv. Which is just this part of it and this part of it. Okay. So if we take the integral of u dv, that's going to equal uv minus the integral of v du. Okay. So if u is equal to the natural log of 4x plus 5, du is equal to the derivative of natural log of x plus 5. And I'll write a little side note over here. Remember, the derivative of the natural log of a function is equal to the derivative of that function divided by that function. So the derivative of the natural log of 4x, let me kind of separate that, 4x to the 5th power, where we know that this is your g of x. So we know that's going to equal g prime of x over g of x. We know that's going to equal the derivative of g of x, which is 20x to the 4th power, divided by 4x to the 5th power. So if we simplify that, we just get 5 over x. Okay, so if our u is natural log of 4 times x to the 5th, our derivative of u is equal to 5 over x with respect to x. Okay, so we have our u, and we have our du. Now we have our dv, now we need our v, because we have to find u, du, v, vd, dv. Okay, so if we take the integral of our derivative of v, that's going to equal the integral of 1 over square root of x with respect to x. Just integrate both sides. So again, we know that the integral of our derivative cancel each other out. So we're just left with our v of x function, which is equal to the integral of 1 over square root of x. But we can rewrite that as x to the negative 1/2 power with respect to x. So if we take our x to the negative 1/2 power, integral of x to the negative 1/2 is x to the negative 1/2 plus 1 divided by 1/2, negative 1/2 plus 1, which is positive 1/2. So x to the 1/2 power divided by 1/2. So if we multiply the numerator and denominator by 2, it's just 2x to the 1/2 power. So we know that our v is equal to 2x to the 1/2 power, or just 2 square root of x. Okay, so we have everything we need here. We have our u, our dv, our du, and our v. Okay, so I'm just going to rewrite this formula so we can place everything underneath it. Kind of separate that a little bit. The integral of u dv equals uv minus the integral of v du. So that's the integral of our u, natural log of 4x, the integral, 4x to the 5th, dv, which is 1 over square root of x dx, is equal to u times v. So we have natural log of 4x to the 5th times 2 square root of x minus the antiderivative of v du. So the antiderivative of 2 square root of x times 5 over x with respect to x. Make that a little bit clearer. There we go. So again, if you notice here, this is just the integral of u dv is equal to u times v minus the antiderivative of v du. Okay. Now this part here, your u times v, that just stays. You don't really have to do anything else with that. You have the natural log of 4x to the 5th power times 2 square root of x. Now for this one, just to make it a little easier, we're going to factor out our 2 times 5, and we're just going to bring that right out to the front and make it 10. And if we multiply square root of x times 1 over x, if we change that x to square root of x times square root of x, it would cancel out one of these. So it would just be 1 over square root of x if we multiply those two together with respect to x. But luckily for us, we've already done that. The integral of 1 over square root of x, which is the integral of x to the negative 1/2 power, is just 2 square root of x. Now, it doesn't always work out like that, but just so happens with this one it did. So you have the natural log of 4x to the 5th power times 2 square root of x minus 10, and this integral here, we just go ahead and replace that with 2 square root of x. Nope, got my plus c. So if we simplify it one final time, you can get the 2 and factor it out to the front if you like. I don't think they'll mark it wrong if you don't. So 2 times the natural log of 4x to the 5th power times square root of x, or you can say 2 square root of x. Doesn't matter which order. Go ahead and multiply the 10 and the 2. You just get minus 20 square root of x plus c. All right, any questions on that one? All right. Anyone still writing? Okay. But if we wanted to evaluate the integral of x times e to the power of x with respect to x. Okay. So again, we can look at it and tell u substitution won't work. You can't use any kind of product rule with integrals. So we have to look at our LIATE. Okay, so logarithmic, inverse, algebraic comes before exponential. So that x term, that's the one we're going to use. I mean, x factor, that's the one we're going to use for our u. We have the integral of x times e to the power of x dx. We're going to make this our u, and this is going to be our dv. Okay, so we know our u is equal to x, which means our derivative of u is going to be 1 dx, or just dx. Okay. And our dv is e to the power of x dx. So if we integrate both sides of our dv, the integral and derivative cancel each other out. So v is just equal to the antiderivative or integral of e to the power of x dx. Yes.
How did the integral cancel? On the left?
Oh, because your derivative and integral, they're inverses of each other. Okay, so we know the integral of e to the power of x is just e to the power of x. And you don't have to worry about the plus c here. We'll add that at the very end if necessary. All right, so now we know that if we take our integral of x times e to the power of x dx, so our integral of u dv is going to equal our u times v minus the integral of v du. Okay. So our u times v is just x times e to the power of x. Minus the integral of v, which is e to the power of x, du, which is dx. And for me, just lining them up like this always helped. At least till you get comfortable with it. And write it out without all the lineups. Equals x e to the power of x minus the integral of e to the power of x dx. This is my own little side note, so now all we have to do, again, this right here is pretty much set. You don't have to do much with this one. But integral of e to the power of x is just e to the power of x. So it's x e to the power of x minus e to the power of x plus c. Or if you wanted to, you could factor out an e to the power of x times x minus 1 plus c. But I don't think Newton cares either way. I think they'll accept both. All right, any questions on that one? All right, anyone still writing? All right. What if we wanted to evaluate the integral of x squared times natural log of x with respect to x? Using integration by parts. Again, if we look at LIATE, the logarithmic function comes first in that list, so we're going to use that as our u. So since that's the u, just for visual effects, I'm just going to switch those around. So natural log of x times x squared dx. Okay, so this gives us our integral of u dv. So that means we have to find our u is equal to natural log of x. About to write u is equal to x. And our du is 1 over x dx. And you put the absolute value there just to be on the safe side. Okay, so we have our u and we have our du. Okay, we know that our dv is x squared dx. So if we integrate both sides, the integral of your derivative of v is equal to the integral of x squared with respect to x. Okay. So the integral of your derivative is just your function, so that becomes your v is equal to the integral of x squared, which is x to the third power over 3. Oops. Okay, so we go ahead and plug all those in. The integral of natural log of x times x squared dx, or your integral of u dv, is equal to u times v minus the antiderivative of v du. Let me kind of separate that so it doesn't get mixed in there. Okay. So u times v is just natural log of x times x to the third power over 3. minus the antiderivative of v du minus the antiderivative of v, which is x to the third power over 3, du, which is 1 over x dx. Okay. So this one, if you want, you can go ahead and rewrite it. X squared dx equal to, we can make that 1 over 3 x to the third times the natural log of x. Whichever order is perfectly okay. Minus, now with this one, we can kind of simplify it. We can still factor out that 1/3. The x to the third power divided by x is just x squared. So the integral of x squared with respect to x. So it's going to equal 1/3 x to the third power natural log of x. As I keep forgetting to write the absolute value, let's just say we know that x is greater than 0. This way I don't have to keep forgetting to write the absolute value. Okay, so we have minus 1/3 times the antiderivative of x squared, which is x to the third power over 3, plus c. So now we can just simplify it by combining those two fractions. So we have 1/3 x to the third power times natural log of x minus 1/9 x to the third power plus c. Any questions on that one? All right, anyone still writing? Okay. So what if we wanted to evaluate the integral of 3x times cosine of x with respect to x using integration by parts? Okay, so again, if we look at the LIATE, we can see that the algebraic function comes before the trig function. Which means for this one, our u is just going to be equal to x. You can factor out the 3 if you want to, or you can make it 3x. You're okay either way. The u is going to be 3x, and your dv is going to be cosine of x dx. So we know that u is equal to 3x. And our derivative of u is equal to 3 dx. And our dv is equal to cosine of x dx. So if we integrate both sides, you know that the integral of the derivative is just the position function. So we have our v, which is equal to the integral of cosine with respect to x, which is equal to sine. So we know that the integral of u dv is equal to u times v minus the integral of v du. So the integral of 3x times cosine of x dx is equal to u times v, so that's 3x times sine of x, minus the antiderivative of v du. So v is sine of x, and du is equal to 3 dx. Okay. Now the 3 here, you can just go ahead and factor that right on out. So we have 3x sine of x minus 3 times the integral of sine of x with respect to x. Okay. Now the integral of sine is just negative cosine. So that gives us 3x times sine of x minus 3 times negative cosine of x plus c. Okay. From there, we can just go ahead and simplify this by making that minus negative positive. So 3x sine of x plus 3 cosine of x plus c. Okay. Any questions on that one? All right. Anyone still writing? Okay. So what if we wanted to evaluate the integral of sine inverse of x with respect to x using integration by parts? Okay. Well, no real need to use the acronym because it's only one function in there. That's your inverse function. So if you wanted to, you don't have to, but if you wanted to, you could rewrite it as sine inverse of x times 1 dx. You don't have to. We know that your u is sine inverse of x. And your dv is 1 dx or just dx. Okay. So u is equal to sine inverse of x. If you remember from Calc 1, your derivative of sine inverse of x is 1 over the square root of 1 minus x squared dx. Okay. And your dv is equal to 1 dx, or I guess you can just say dx. That's perfectly fine. So if we integrate both sides, and we know that v is equal to the integral of of 1 dx or just dx, the integral of, let's say, 1 dx, if you want to put a 1 in there, which is just x. That's why I was saying the 1 is optional. Sometimes it helps to visualize. Okay, so if we have the integral of u dv equals uv minus the integral of v du, we plug everything in, and that's the integral sine inverse of x dx is equal to u times v, which is sine inverse of x times x, but I'll just write it as x, sine inverse of x. And the next step, I'll put it in the same order just to avoid confusion. So sine inverse of x times x minus the antiderivative or integral of v du. So that's x times the square 1 over the square root of 1 minus x squared dx. Now your x times the square root, well, 1 divided by the square root of 1 minus x squared dx, we can actually solve that through u substitution. And I'll just put that right under here. So if we have our integral of 1 over the square root of 1 minus x squared times x dx, we'll let u equal 1 minus x squared. And our derivative of u is going to equal negative 2x dx. So if we divide both sides by negative 2, we have negative 1/2 du is equal to x dx. Okay, so if we take our original integral here, and we can rewrite that as 1 minus x squared to the negative 1/2, since the square root is in the denominator. We can rewrite that as the integral of u to the negative 1/2. So we got my half line, u to the negative 1/2. And our x dx, that's our negative 1/2 du. Okay, so that negative 1/2, we can go ahead and just factor that right out to the front. U to the negative 1/2 du. Okay, so that becomes a negative 1/2. And the integral of u to the negative 1/2 is u to the negative 1/2 plus 1 power divided by negative 1/2 plus 1, which is positive 1/2. So u to the positive 1/2 divided by 1/2. And we can put the plus c on there just to be safe. So if we multiply this one, actually, we don't even have to multiply by anything, because 1/2 and 1/2 cancel each other out. I was going to multiply it by 2, but we'd end up with the same thing anyway. So we have negative u to the 1/2 power plus c. So we just replace our u with 1 minus x squared, and that's just negative 1 minus x squared to the 1/2 power plus c. Okay, so that gives us the integral of sine inverse of x dx is equal to x times sine inverse of x minus, and this entire integral is just minus negative 1 minus x squared to the 1/2 power plus c, where that minus negative, we can go ahead and make that positive. So x times sine inverse of x plus 1 minus x squared to the 1/2 power plus c. Or you can make that square root of x if you want to. X times sine inverse of x plus square root of 1 minus x squared plus c. Just in case Newton decides to act funny about the 1/2 exponent. All right, any questions on that one? All right. Anyone still writing? Okay, so what if we wanted to evaluate the integral of 7x squared times e to the power of 2x with respect to x using integration by parts? Okay, so again, we look at our LIATE. We can see that the algebraic expression comes before the exponential. So our u is going to be our 7x squared. Unless you decide to factor out the 7, then it's just x squared, but I usually just keep the 7 in there. Because if you factor out the 7, you have to remember to put the 7 at the beginning of it on each step. And sometimes that can get a little bit tricky. When you're doing all this other stuff, that's one more thing to remember. So I just usually leave it in there. Okay, so for our 7x squared e to the power of 2x dx, this is our u, and this is our dv. Okay, so u is equal to 7x squared. Our derivative of u in differential form is, bring down the 2, 7 times 2 is 14, so that's 14x dx. Our dv is equal to e to the power of 2x dx. So if we integrate both sides, we know that our v is equal to the integral of e to the power of 2x with respect to x. Okay, so we know v is equal to 1/2 e to the power of 2x. So for those steps, we just see that the integral of e to the power of 2x with respect to x, if we let u equal 2x and du equals 2 dx, we divide both sides by 2, du over 2 is equal to dx. Then we can rewrite this as e to the power of u, and that dx, we replace that with du over 2. So that gives us 1/2 times the integral of e to the power of u du, which the integral of e to the power of u with respect to u is just e to the power of u. So 1/2 e to the power of u plus c. So if we go ahead and replace our u, that's just 1/2 e to the power of 2x plus c. So we know our v is equal to 1/2 e to the power of 2x. And again, we're going to add our c at the very end, so no point in dragging it along for each step. So we know that the integral of u dv equals uv minus the integral of v du. So u times v is 7x squared times 1/2 e to the power of 2x. Minus the integral of v du. So v being 1/2 times e to the power of 2x. And du is 14x dx. And we'll just put the 14x in parentheses. Okay, so if we go ahead and combine these two, we just get 7. And if we go ahead and combine these two, we just get 7 over 2. So we can go ahead and simplify that right here. So we have 7 over 2 x squared e to the power 2x. Minus that 14 times 1/2, that's just 7. We're going to go ahead and bring that right out to the front here instead of worrying about it later. So that leaves e to the power of 2x times x times the integral of x times e to the power of 2x dx. Okay, now with this one, and you'll probably run across this quite a few times, you actually have to use integration by parts again. There are a lot of problems where you have to use integration by parts multiple times. Okay, so the u, du, dv, and v up here, you can kind of ignore them. You're going to start a whole new different set of u, dus, v's, and dv's. That's just for this one. Okay, so again, we see the algebraic expression comes before the logarithmic one. So we're going to make our u equal to x. And the derivative of u with respect to x is 1 dx, or just dx. So your dv is equal to e to the power of 2x dx. And luckily enough, we have that right up here. So we know that v is equal to 1/2 e to the power of 2x. Said that doesn't always happen, but when it does, it saves you a little bit of work. Okay, so our integral of u dv equals uv minus the integral of v du. So the integral of x e to the power of 2x dx is equal to u times v, which is x times 1/2 e to the power of 2x, minus the integral of v du. So 1/2 e to the power of 2x dx. Okay, so we can go ahead and simplify this. We can just make that 1/2 x e to the power of 2x minus, we can go ahead and factor out that 1/2 e to the power of 2x dx. Okay, well, luckily for us, we already know what this part is. So that's going to equal 1/2 times x times e to the power of 2x minus 1/2 times the integral of e to the power of 2x, which we know is 1/2 e to the power of 2x. Plus c. Oops, straighten that up there. All right, so go ahead and simplify this by combining those two. You know, the integral of x times e to the power of 2x dx is equal to 1/2 times x times e to the power of 2x minus 1/4 e to the power of 2x plus c. And we'll continue this on the next page. Excuse me. Oh, here it is. All right, anyone still writing? All right. Okay, so let me kind of rewrite the steps so it can get a little bit messy here. So starting off, we knew that the integral of 7x squared e to the power of 2x dx, we knew that was equal, oh, there we go, to 7 over 2x squared times e to the power of 2x minus 7 times the integral of x times e to the power of 2x dx. Okay, and when we had to do integration by parts for this portion of it, so might help if I kept that to write it down. And that just became, move this over, 7 over 2x squared times e to the power of 2x minus 7 times the integral of x times e to the power of 2x, which ends up being 1/2 x times e to the power of 2x minus 1 over 4 e to the power of 2x plus c. Straighten that up a little bit. Okay. So now we just have to distribute that -7. So we have 7 over 2x squared e to the power of 2x minus 7 over 2x times e to the power of 2x plus 7 over 4 e to the power of 2x plus c. It does have the tendency to sometimes get a little lengthy, depending on how many times you have to use integration by parts in the same problem. Any questions on that one? All right, anyone still writing? Okay, now with this one, what if we wanted to evaluate the integral of secant cubed with respect to x using integration by parts? Okay, now with this one, secant cubed with respect to x, you can just rewrite it. So the integral of secant of x times secant squared of x with respect to x. That's because we know there's an integral of secant squared out there. So when you have both trig functions, usually use the lower exponent as your u. Okay, so this will be our u, and this will be our dv. Yes.
So you always just get it by itself, one of the other trig functions?
You mean, you mean just to factor out
Yeah,
one of,
factor out just one?
yes.
Okay.
Okay. So we know that u is equal to secant of x. And we know that the derivative of secant is secant times tangent. And we know that our dv is secant squared dx. And our v is equal to the integral of secant squared of x dx. And so we know that v is equal to tangent of x. So if we take the integral of u dv is equal to u times v minus the integral of v du, we know the integral of secant times secant squared with respect to x is equal to u times v, which is secant times tangent, minus the integral of v du. So v is tangent of x, and du is secant times tangent dx. Will I have enough room? You know what, I'll put this below it just because I know I'm going to run out of room. Secant tangent. That's the antiderivative of tangent of x times secant. Secant tangent. And don't tell me I'm going to run out of room anyway. Dx. Didn't bring it over far enough. Tried to somewhat have it lined up with that one. Okay. Now we can go ahead and combine the two tangents and just make it tangent squared. So we have secant of x times tangent of x minus the integral of tangent squared times secant with respect to x. Okay, so it gives us secant. So I can make a little bit of room because I'm going to write a little note below this. Because we know that tangent squared, we could rewrite that as secant squared minus 1. So that gives us secant of x times tangent of x is equal to the antiderivative of secant squared of x minus 1. Oh, why'd I put equal and minus? Times secant of x with respect to x. So now we're going to go ahead and distribute that secant. That's going to equal secant of x times tangent of x minus the integral of secant cubed of x minus secant x. We can also, we'll just put those together. I'll do that on the next step. Okay. Okay. So if we distribute this -1 and the integral to both of those terms, move this over just a little bit. Okay. So remember, this just keeps on coming right on down. Instead of writing it over and over and over again. I'm going to bring that over a little because I can see this cutting off at the end. So you have secant of x times tangent of x minus the integral of secant cubed of x with respect to x plus the integral of secant of x with respect to x. And remember, this all started with the integral of secant cubed of x dx. So if you look in here, you have that minus secant cube of x, and you have that positive secant cube of x. So if we add the integral of secant cubed of x dx to both sides of the equal sign, you kind of separate that a little bit. These are its own little personal group of steps. Then that gives us 2 times the integral of secant cubed of x with respect to x. And these two on the right, they just cancel each other out and become 0. So that's going to equal secant of x times tangent of x plus the integral of secant of x dx. Okay, well, this integral, we know that this is just the natural log or negative natural log of secant x plus tangent x. And I'll go ahead and continue on the next page instead of trying to squeeze everything here. Over a little bit, there we go. All right, anyone still writing? Oh, I see. You're all set? Okay. Anyone else still writing? All right. Okay, so if we write down where we left off, you have 2 times the integral of secant cubed with respect to x is equal to secant times tangent. And that integral of secant, we can go ahead and replace that with negative natural log of secant plus tangent. Oops. Plus c. So now to solve for the actual integral of secant cubed, we're just going to divide each term by 2. And a constant divided by 2 is still a constant. So those 2's cancel each other out. So we are left with the integral of secant cubed is equal to 1/2 secant times tangent minus 1/2 the natural log of the absolute value of secant plus tangent plus c. So that one has a little bit of trickery in it. All right. Any questions on that one? Yes.
For the natural log part, was it negative or like subtracting that natural log or adding it?
Oh, it was negative, but it was the integral of secant is negative natural log. So that positive just became that negative. You're welcome. All right. Anyone still writing? Okay. Okay, so with this one, this is kind of a shortcut for integration by parts. I would still learn integration by parts because a lot of professors do not want you using this shortcut. So I would use it for like homework and stuff like that. But on an exam, some of them actually want to see you use integration by parts. So I'm one of the few that I'm perfectly okay with you using the shortcut. It's called the tabular method. And it's also known as Kroneker's method. I think they stopped calling it Kroneker's method a while ago. I think I was still in college when they were calling it that. That was a while ago. Okay, so let's say, just for example, we want to evaluate the integral of 2x squared times e to the power 4x with respect to x. So I'm kind of going into detail, but as you practice it, you'll get really familiar with it and get a little speed to it. You won't have to take up as much room. Okay, so the first thing you're going to do is you're going to create a column create a table with 3 columns. I'm jumping ahead. Create a table with 3 columns. There we go. Okay. Now your first column we have your signs. And always go plus or positive, negative, positive, negative, positive, negative, and however many columns you have. Your second column, you're going to repeatedly differentiate your U. And separate those a little bit. In your third column, you're going to repeatedly integrate your DV. Okay, so if you create your table, and that should be big enough. Okay, your first column is going to be your signs. Positive, negative, positive, negative. I'm always going to start with positive. And I'll add one more. Okay, now you're going to differentiate your U. Okay. And again, using the LIATE, we know that the algebraic function comes before the exponential function. So our U is going to equal 2x squared. Might as well take this all the way to the end. There we go. Now you take the first derivative of U, which gives you 4x. Then you take the second derivative of U, which is 4. You take the third derivative, which is the derivative of U, but the derivative of 4, which is just 0. And you, of course, you can stop there once you hit 0. Okay. Now we're going to integrate your dv. Okay. So we know that our dv is equal to e to the power of 4x dx, because we have our u dv. Which means our v is equal to the integral of e to the power of 4x dx. So if you integrate this once, we'll call this v number 1. You get 1/4 e to the power of 4x. So now you integrate this one. So you have, we'll call this v number 2, which is 1/4 times the integral of e to the power of 4x dx, which is 1/4 times 1/4 e to the power of 4x, which is 1/16 e to the power of 4x. And I thought I had enough room. Take it all the way to the end. Here we go. So 1/16 e to the power of 4x. Okay. Now you integrate that one. So our v number 3 is just 1/16 times the integral of e to the power of 4x. So that's just 1/16 times 1/4 e to the power of 2x, which is 1/64 e to the power of 2x. I mean, e to the power of 4x. Why do I keep saying 2x? Let me move that over so it doesn't blend in with the end of the column. E to the power of 4x. Here we go. Okay. And this one, you actually don't even bother with it. We could just keep on going, but we know we won't have to be bothered with that one, because you're going to join the sections diagonally. Okay, so you're going to combine these two boxes, these two, and these two. The reason we didn't have to bother with this one, because you're going to multiply 0 times whatever that is, and it would have just been 0. So we didn't even have to bother with it. Okay, so we know that the integral of 2x squared times e to the power of 4x dx is equal to positive 2x squared times 1/4 e to the power of 4x. Minus 4x times 1/16 e to the power of 4x. Plus 4 times 1/64 e to the power of 4x. And again, once you hit 0, you don't even have to worry about it, so it's just plus c. Okay, so now all we have to do is simplify it. We have 2 times 1/4, which is 1/2. So we have 1/2 x squared e to the power of 4x. 4 times 1/16 is 1/4. So that's minus 1/4 x e to the power of 4x. Plus, we have 4 divided by 6, well, times 1/64 is 1/16. So we have 1/16 e to the power of 4x plus c. And you can always double check it using the regular integration by parts. But we can tell you're going to have to do the integration by parts over and over and over again, just by the number of terms in the answer. Yes.
When using the table, how do we know if we're supposed to start with a positive or a negative, or is it just based off of what we are differentiating?
Yep, we're always going to start off with positive. Now, this would have been negative 2x squared, then it would have turned into negative.
Okay.
But this always starts positive. You're welcome.
So if it was negative, you would just write negative 2x squared in there.
Yep, exactly. So it would have been positive, and then it would have just been, this whole thing would have just been negative 2x squared. All right, any other questions on this one? All right, one more example just to kind of reinforce the steps. Oh, anyone still writing? Okay. So if we wanted to evaluate the integral of 4x times e to the power of negative 5x with respect to x. You're still going to need our LIAT. So we know that our u would have to be 4x because our algebraic term comes before our exponential. So again, your first column will be your signs. So it's going to be positive, negative, positive, negative, positive. I don't think you'll need that many rows, but just in case. So second column, we're going to differentiate our u. And I should be able to make this a pretty narrow column. So we know u is equal to 4x. So our first derivative is just 4, and our second derivative is 0. So yep, we didn't need any more columns. Any more rows. And the third one, we're going to integrate your dv. Okay, so we know that our dv is e to the power of negative 5x dx. That means that v is equal to the integral of e to the power of negative 5x. So if we integrate that, that'll be our first integration, which is negative 1/5 e to the power of negative 5x. And if we integrate this one, that's negative 1/5 times the integral of e to the power of negative 5x. So that's just negative 1/5 times negative 1/5 e to the power of negative 5x, which is positive 1/25 e to the power of negative 5x. Because we already know what this is equal to, which is this up here. Okay. And again, we can stop there because remember, we're going to multiply them diagonally. So this is 0, we just multiply to whatever is here, so it doesn't matter what that is. So we can actually stop there. So we know the integral of 4x e to the power of negative 5x dx is equal to 4x times negative 1/5 e to the power of 5x. So that's plus, then minus 4 times negative 1/5 e to the power, well, that's the integral, so that's positive 1/25 e to the power of negative 5x. And since that's the last one, you just make it plus c. And then from there, you just simplify. And this is what you were talking about when you said the first one will always be positive. This is the example when it just changes over. So 4 times negative 1/5 is negative 4/5 times x e to the power of negative 5x. And this second one is minus 4, should put it as 4/25 e to the power of negative 5x plus c. Now, this is your last math class. I'm perfectly okay with you using this all the way through. I'm fine. But if you have more math classes you have to take, I would still get very comfortable with integration by parts, because you will run into some where you say solve it only using integration by parts, because some of them really hate this method. So for me, I don't see what the big deal is. It's why spend 25 minutes working on something when you can get the same answer in 5. So, but just kind of a warning. So if you go, well, you didn't tell me I had to learn it. No, I'm telling you now, if you have more math classes, I would definitely learn the regular method, integration by parts. So. All right, any questions on that one? Yes.
Is there any one of the LIATE that doesn't work for this method, or do they all work?
With this one, it will repeat, like with the secant cubed. If you find the one that repeats, you do have to be careful with those, because then this won't become 0. So if you have like a sine or a cosine, the derivative of that would just keep repeating over and over. So you do have to be careful with that. And eventually you'll find it to where you have that integral with the cosine, you'll see it repeat, and then you just have to add it to both sides. So that's the only really hiccup with that one. You just have to be careful with that. You're welcome. But yeah, anyone that eventually differentiates the 0, pretty straightforward. Any other questions on this one? All right. Oh, anyone still writing? All right. Okay, so now we're going to start on section 7.3. Which kind of looks at the trig integrals. So like that secant cubed, this is just another way you'd be able to solve that one without using integration by parts. Okay. So let's say if you have your exponents some letter m, not some letter, some value m and some value n. And we're looking at the integral of cosine to the power of m of x times sine to the power of n of x with respect to x. So let's say if n happens to be an odd number. Then you're going to subtract one n out of that one. I mean, one exponent out of that one. So you're going to rewrite sine to the power of n of x as sine to the power of n minus 1 of x times sine of x. So if you have sine to the 9th power, you're going to rewrite it as sine to the 8th power times sine to the 1st power. So it's kind of like rewriting x to the 9th power as x to the 8th power times x. Okay, now once you do that, then you're going to use the fact that sine squared of x is equal to 1 minus cosine squared of x. Okay. Now, in most cases, once you're there, you're going to use u substitution. So if nothing else, this class will get you really, really, really fluent in u substitution. Okay. Now let's say if m happens to be odd. You're going to do somewhat the same thing. You're going to rewrite cosine to the power of m of x as cosine to the power of m minus 1 of x times cosine of x. And you're going to use cosine squared of x is equal to 1 minus sine squared of x. Okay. And both of these just come from sine squared plus cosine squared is equal to 1. We just subtract sine squared from both sides or cosine squared from both sides. Now, if m and n are both even, then we're going to use the trig identities. Sine squared of x is equal to 1 minus cosine of 2x divided by 2, and cosine squared of x is equal to 1 plus cosine of 2x divided by 2. And solve. Okay, so if nothing else for this section, make sure you, like I said, with sine squared plus cosine squared is equal to 1, you can pretty much remember those two. But I would definitely write these down and keep them handy if you don't have them memorized, because you will need them. All right. Now with these all fall under the where m is greater than 1 and m is greater than 1. Because if they're equal to 1, there's really not that much of a change. I'll show you the first example when it equals to 1, or when either one of these equal to 1. Anyone still writing? Okay. So let's say, for example, if we wanted to evaluate the integral of sine of 2x times cosine to the 4th power of 2x with respect to x. Okay. And when this exponent is odd and it's just 1, you don't really have to worry about all those steps. All you have to do is remember that if you have cosine to the 4th power of x, you can x of 2x. You can rewrite that as cosine of 2x to the 4th power. You don't have to, but you can. For me, it just visually made it a little easier. And we know that the derivative cosine of x, even though it's 2x, I'm just putting the general cosine of x, is equal to negative sine of x. So of course this would be negative sine of 2x, but okay. So what if we let's say we have our cosine to the 4th. Actually, I'll rewrite it just to make it a little easier. Say cosine of 2x to the 4th power times sine of 2x with respect to x. Okay, so we can let u equal our cosine of 2x. Only because now we can make that u to the 4th power. Okay, and our derivative of cosine of 2x is equal to negative sine of 2x times the derivative of 2x, which is just 2. So our du is just equal to negative 2 sine of 2x. So if we go ahead and divide both sides by negative 2, we have du over negative 2 is equal to sine of 2x. Oh, forgot my dx. Should be dx at the end of those. Right. So this just becomes the integral of u to the 4th power. And this just becomes du over negative 2. So if we factor out that negative 1/2, that's just the integral of u to the 4th power du. So if we go ahead and integrate that, that gives us negative 1/2 times u to the 5th power over 5 plus c. And we can go ahead and multiply those two denominators. We have negative 1/10 times u to the 5th power plus c. So now the only thing left here is just to replace the u. And that gives us negative 1/10. And u is cosine of x. So that's cosine of x to the 5th power plus c. Oh, but I keep forgetting that too. So when your odd exponent is 1, you can kind of ignore all those steps. You can just do it this way, and it's a lot easier. All right, anyone still writing? Okay. So let's say if we wanted to evaluate the integral of cosine squared of x times sine of x to the third power with respect to x. Excuse me. Okay, so we can see for this one, this is our odd exponent. Okay, so since it's our odd exponent, we're going to take that sine of x to the third power, and we're going to subtract 1 from it. So it's sine squared of x times sine of x. Give that a little more room. There we go. So all we did was factor out one of them. And after we do that, we also just have to remember that sine squared plus cosine squared is equal to 1. Subtract cosine squared from both sides. We have sine squared. Of course, you can put the x there, but I was just running out of room. Of x is equal to 1 minus cosine squared of x. So that sine squared, we're going to replace it with 1 minus cosine squared of x. So sine cubed of x is going to equal 1 minus cosine squared of x times sine of x. Okay. So this is basically all you have to do from that first page. This is telling you everything you have to do in one step. You're just going to rewrite it, then subtract 1, and then replace the sine squared with 1 minus cosine squared. Okay, so we started off with the integral of cosine squared of x times sine of x to the third power with respect to x. Notice that this was our odd exponent, so we factored 1 out and replaced the sine squared. So that gave us the integral cosine squared of x times 1 minus cosine squared times sine of x with respect to x. Okay. So for me, I always rewrite it just because it makes the u substitution kind of make a little more sense. So that's the integral cosine squared. We're just going to rewrite that as cosine of x squared times 1 minus cosine of x squared times sine of x with respect to x. Okay, so now we can let u equal cosine of x. Well, we know the derivative of cosine is negative sine. So that means our du is equal to negative sine of x dx. So you can either multiply or divide both sides by -1. Doesn't matter. I usually, when there's no value or no coefficient other than 1 or -1, I just multiply both sides. So negative du is equal to sine of x dx. Okay, so we use that for this step here. Made that longer than I needed. Might as well erase it. There we go. Okay. So now if we just go ahead and replace all of those, that cosine of x squared is just u squared. Oh, put my squared on the outside when it should have been on the inside. There we go. So it should be cosine of x squared, then the parentheses. Okay, so times 1 minus u squared. And that's sine of x, that's negative du. So from there, all we have to do is distribute our u squared and factor out that -1. So that's negative the integral of u squared minus u to the 4th du. And then from there, we just integrate both terms. The integral of u squared, oh, why did I put that down again? I already integrated. Is u to the 3rd power over 3 minus the integral of u to the 4th power, which is u to the 5th power over 5 plus c. So if we go ahead and distribute that negative, we end up with negative 1/3 u to the 3rd power plus 1/5 u to the 5th power plus c. Now once we're there, all we have to do now is just replace u. And our u is equal to cosine of x. So that means we have negative 1/3 of u to the 3rd power. So that's cosine of x to the 3rd power plus 1/5 times u to the 5th power. So that's cosine of x to the 5th power plus c. All right. Any questions on that one? All right. Anyone still writing? Okay. Let's say, for example, if we wanted to evaluate the integral of cosine to the 5th power times sine squared with respect to x. Okay, you can see here that this cosine of x, that's our odd exponent. So that means we're going to take our cosine of x to the 5th power, and we're going to rewrite it as cosine of x to the 4th power times cosine of x. Okay, so again, we know that sine squared equals 1 minus cosine squared. We also know that cosine squared is equal to 1 minus sine squared, which, since cosine is our odd one, we're going to use that one. Now, the only thing is, this is to the 4th power and not squared. So what we're going to have to do, take our 5th cosine of x. Since that's to the 4th power, we're going to make that cosine squared squared. Times cosine of x. So now we can go ahead and replace this with 1 minus sine squared. So this ends up being 1 minus sine squared of x squared times cosine of x. Okay, so we started off the integral of the cosine of x to the 5th power times sine squared of x with respect to x. Then we could go ahead and replace cosine of x to the 5th power with 1 minus sine squared of x squared times cosine of x. And we still have that sine squared of x, so we have to move that down, times sine squared of x with respect to x. Okay, now with this one, just for, like I said, just visual purposes, I'm just going to swap those two. 1 minus sine squared of x squared times sine squared of x times cosine of x dx. Now for this one, since sine of x is now the only one that's raised to a power other than 1, we're going to let u equal sine of x. And the derivative of sine is cosine, so our derivative of u is equal to cosine of x dx. So now if we replace everything, that gives us 1 minus u squared times u squared, which is our sine squared here. And that cosine of x with respect to x, that's our du. So that just becomes du. Okay. So now we just have to expand our 1 minus u squared squared. So 1 minus u squared squared, that's just 1 minus u squared times 1 minus u squared. So if we go ahead and do the FOIL method, that gives us our first is 1. Our outer is negative u squared. Our inner is negative u squared, so it's negative 2u squared. And our last is positive u to the fourth. So that gives us the integral, and that 1 minus u squared squared, we can just replace that with 1 minus 2u squared plus u to the fourth. So that's still multiplied by u squared, so we just put that u squared right there and bring down our du. Okay, so now we can go ahead and distribute that u squared. So you have the integral, u squared times 1 is u squared, minus 2 times u squared is minus 2u to the fourth, plus u squared times u to the fourth is u to the sixth power with respect to u. Okay, so now that we have all those exponents and stuff gone, we can just integrate each term. So the integral of u squared is u to the third power over 3, or you can just say 1/3 u to the third power, minus 2 times the integral of u to the fourth power, so it's minus 2 times u to the fifth power over 5, you can say 1/5 u to the fifth power, plus the integral of u to the sixth power, so it's u to the seventh power over 7, or you can just say 1/7 u to the seventh, plus c. Okay. And from there, we can just go ahead and replace u. So our u is sine of x. So that gives us 1/3 times sine of x to the third power, minus 2/5. If we go ahead and multiply negative 2 and 1/5. So minus 2/5 times sine to the 5th power plus 1/7 times sine to the 7th power plus c. All right, any questions on that one? All right, anyone still writing? Okay. Okay, so what if we wanted to evaluate the integral of cosine to the 48th power of x times sine of x to the 3rd power with respect to x? Okay, now no matter what, you're always going to look at the odd exponent, no matter how big the even one is. You're always going to focus on the odd one first. Okay, so we know that sine of x to the 3rd power, we're going to factor 1 out of it. So it's just going to be sine squared of x times sine of x. And that sine squared, we're going to replace that with 1 minus cosine squared. So that means our sine to the 3rd power of x is equal to 1 minus cosine squared of x times sine of x. So that integral of cosine of x to the 48th power times sine to the 3rd power of x with respect to x. We're just going to rewrite that. Have cosine of x to the 48th power. And that sine of x to the 3rd power, I'm going to make that 1 minus cosine squared of x times sine of x. With respect to x. Okay, so now sine is the only one that doesn't have an exponent other than 1, so we're just going to make u equal cosine. Let me clean that up a little bit. There we go. Okay. Now, derivative of cosine is negative sine, so our du equals negative sine dx. And if we multiply both sides by -1, we know that negative du is equal to sine of x dx. So now we just go ahead and rewrite it. Now this just becomes u to the 48th power. So we have the integral of u to the 48th power times 1 minus cosine squared. That just becomes 1 minus u squared times sine of x dx. Well, that's our negative du. So that negative 1 from the du, we can factor that right out to the front. And that u to the 48th power, we can just go ahead and distribute that right to both of those terms. That's going to be u to the 48th power minus u to the 48th power times u squared is u to the 50th power du. Okay. Then we go ahead and integrate both of those terms. So we bring down our negative. So the integral of u to the 48th power is u to the 49th power over 49. I could have wrote it 1 over 49 times that, but this is okay. Minus the integral of u to the 50th power is u to the 51st power over 51 plus c. All right, so if we go ahead and distribute that negative, that's negative 1 over 49 times u to the 49th power plus 1 over 51 times u to the 51st power plus c. And then from there, we just go ahead and replace our u. So that gives us negative 1 over 49 times u to the 49th power. Our u is cosine. So that's cosine of x to the 49th power plus 1 over 51 times cosine of x to the 51st power plus c. And make that a little bit neater. That didn't help. F to the 51. There we go. All right. Any questions on that one? All right. Okay. We have enough time for one more example. Anyone still writing? Okay. And what if we wanted to evaluate the integral of cosine of x to the 4th power? Okay, now in this case, we have an even exponent. So since it's even, we have to replace cosine squared of x. I'll just put equal to instead of replace it with, which is equal to 1/2 plus cosine 2. I can actually put it over 1 instead of breaking it down to two separate ones, which we could still do. 1 plus cosine of 2x over 2. Which, if you wanted to break it down, you could just say 1/2 plus cosine of 2x over 2. I didn't plan on writing both, so I didn't plan on enough space. Cosine of 2x over 2. Okay. So we have cosine of x to the 4th power. But remember that cosine of x to the 4th power, we could rewrite that as cosine squared squared. Okay. Same way if you had x to the 4th power, you can rewrite that as x squared squared. Same rules apply. Okay. Now we're going to replace our cosine squared. So that means that cosine of x to the 4th power is going to equal cosine squared squared. And there's a reason I separated this is because then we can do the FOIL method when it's in two terms. Where here, we'd just be able to multiply the denominators. We'd still have to do the FOIL method on the numerator. So that's 1/2 plus cosine of 2x divided by 2 squared. Let me make this squared a little clearer just to make sure. There we go. Down, there we go. Okay, so we know that we have 4th cosine of x is equal to 1/2 plus cosine of 2x over 2 squared. So that's 1/2 plus cosine of 2x over 2. So we can go ahead and use the FOIL method on this one. So our first is 1/2 times 1/2, which is 1/4. I was about to say 1 to the 4th for some odd reason. Our outer is 1/2 times cosine of 2x over 2. Yep, which is 1/4 cosine of 2x. Our inner is 1/2 times cosine of 2x over 2, which is plus 1/4 cosine of 2x. And our last is cosine of 2x times cosine of 2x over 2, which is plus cosine of 2x squared over 4, or 1/4 cosine of 2x. Squared. Go ahead and combine those two middle terms. So that's going to equal 1/4 plus 1/4 plus 1/4 is just 2/4, so it's 1/2 cosine of 2x plus 1/4, and that cosine squared of 2x, we're going to replace that back with our cosine squared formula. So it's going to be 1/4 times 1/2 plus 1/2, and since it's cosine squared of 2x, that's going to be cosine of 2 times the x, which in this case the x is 2x. Cosine of 2 times 2x. So that's the little tricky part there. So that gives us 1/4 plus 1/2 cosine of 2x. And if we distribute that 1/4, it gives us 1/8 plus 1/8 times cosine of 4x. And if we go ahead and combine those two, we end up with 3/8. So cosine of x to the 4th power is equal to 3/8 plus 1/2 cosine of 2x plus 1/8 cosine 4x. So if we integrate both sides, the integral of 3/8 is 3/8 times x plus 1/2 times the integral of cosine of 2x is 1/2 sine of x, well, sine of 2x, plus 1/8 times the integral of cosine 4x is 1/4 sine of 4x plus c. Okay, so now we just simplify, and that gives us 3/8 x plus 1/4 sine of 2x plus 1/32 times sine of 4x plus c. Okay, so you only have to do this when you have an even exponent, or they're both even, or in this case, you have only one and it's even. All right. Sorry I kept you over a little bit. I miscalculated just how long that problem would take. All right. So if you have questions, feel free to ask away. I'll be here for a little while checking in with Canvas. If not, enjoy your break. Do not come in on Monday.
Have a good day.
All right, you too. I'll see you on Tuesday.
There's no class Monday?
Nope, no class Monday. Oh, I'm so glad I mentioned that again.
Have a great rest of your day.
All right, you too.
So I won't be here Tuesday.
Oh, okay.
I'm flying home from California.
Oh.
So that's what's going on. I was just wondering, can you give me a brief overview of
All right, you have a
what,
good one.
of what the class is going to be? Because I wasn't here Monday
Mhm.
or Tuesday because I wasn't admitted Monday,
Mhm.
and then I got admitted Tuesday, and then I got registered into the class late. So
Oh, okay.
I'm just confused on, like when the exams are and if this is a calculator class where I get to use a calculator
Oh,
on
yeah,
the
you can.
test.
Yeah, you
Okay.
can. All right, so the exam, the very first exam will be after, let me see if I can, after section 7.2. So we're not done with 7.2 yet. We're just kind of getting started on it. But as soon as we're done with 7.2, the exam will be after that.
Okay.
So if you look on the syllabus, where is it? Kind of give a quick overview. Where is it? Here we go. Okay, so you can kind of go through there. All right, you too. Okay. So it kind of tells when all the exams are, and they'll
Okay.
be online. So if you're out of town or somewhere else, you can always take it online.
Okay.
And the only one that you'd have to come onto campus to take will be the final.
Okay.
All right. So again, which sections will be covered by each one.
Okay.
All right. And let me see where else. And I have the lecture videos. As soon as we take it and we're done with it, they appear down here. But for some reason, students aren't able to see them.
Okay.
So I created a link that did work for like a day. Then it stopped. So
Okay.
I'll basically have to contact them again and say, hey, why isn't this working again? So I'll be here for a minute. So if you have any
Okay.
questions,
All
feel
right.
free to pop in and ask.
Yeah. And then I haven't gotten a chance to take a look at the homework yet, but what is the homework like, and
Oh, yep. You just click
when are
on-
they normally just due?
Well, this one, because after the first week, I usually give like a little bit of time in case we get students who enroll late.
Okay.
So this one isn't due till Monday. So if you click on there,
Oh, it's not due till Monday.
yeah,
I thought it
Monday
was-
at midnight.
Okay.
So, yep.
I thought it was due Friday tomorrow night.
Oh, nope, you are good.
Okay.
What is that? Oh, wait a minute. Let me double check because I could have sworn I said it for Monday. Let me make sure. I meant to make that the 25th.
Okay.
No, I'm glad you said something. Yeah, because I meant to make that due on Memorial Day. Let me change that. Okay. All right, so yep, you can get those, and as soon as you're done with those, they're all just submitted as soon as you
Get them
enter
done.
it. Yep,
Okay.
as soon as you enter it.
All right.
And let me see what else might be. Yeah, for some reason, like I said, it doesn't work now, but the one I just did earlier. Nope, I had that one working earlier. I did it right at the beginning of class and it worked. I don't know why it's not working now. That's why technology, you can love it and hate it at the same time.
Yeah.
All right, so yeah, I'm going to try and get a hold of them and find out why this is not working again. So
Okay.
So
Sounds
yeah,
good.
if you have any questions, feel free to let me know. My email, I check that maybe about twice a week, so that's not the fastest way to get a hold of me.
Okay.
If you email me directly through Canvas, I'll see that, and usually either at the end of the day or beginning of the day, I try to check them. But
Okay.
sometimes if I'm like in a hurry to leave out, I'd get until the next day. But it's usually a lot faster to reach me
All right.
through Canvas.
All right. Sounds good.
All
Thank
right?
you.
You're welcome. All right, have a good trip.
Thank you.
I know what you meant. I know instant
Have a
response.
good day.
You too.